All right, hello again, everybody. So in this one, we're going to take a look at a new data structure called linked lists, but we'll start off with a review of like the big O runtimes of some operations on vectors. So for example, like when you create a vector of a particular size here, technically the creation is constant time, but usually, when you create a vector, you want to fill it with zeros or something like that. So that involves a loop that takes O of n time to actually fill it with values there like that. But when you destroy a vector, right, to destroy a vector, the destructor is literally just going to be a single delete on the sort of underlying array. So that's going to take a constant amount of time there. Vectors store their size. We have that int sz variable. So the size function just returns that. That takes a constant amount of time. And under the hood, a vector is just an array. So to subscript on a vector is the same as an array. It's just an O of 1 time there like that. In the previous video, we looked at pushback, right? How does that sort of work there? And we found that that is O of 1 amortized, but O of n in the worst case there like that. A pop back, though, is literally just decrementing the size. Like we don't literally, like if we want to remove the last element of a vector, we don't actually need to like remove anything. We just pretend that it's not there by decrementing the size, and that takes a constant amount of time. Now, vectors don't actually support these as real operations, but you can imagine a push front and a pop front there that add and remove elements to the beginning of a vector. Last time we looked at a double-ended vector, which tries to make those operations fast, but the normal vector doesn't do that. It doesn't try to make push front and pop front fast. So to add a new element to the beginning of a vector would require a loop to shift everything forward to make room for it, and that would take O of n time there. Same thing for like, if you want to do a pop front, if we want to erase the first thing in a vector, you need to do a loop to shift everything down to fill in the empty space. So that would take O of n time there. If you want to insert an element in a vector at position I, then everything after I, the n minus 1 items that are after I, those need to get shifted up. So you need a loop to do that. If you want to erase the ith element from a vector, then the n minus I elements after that need to get shifted down there. So these sort of last few operations here, these all for vectors involve looping. So they're all going to be O of n or something like that there. So from the table, you can kind of see that, like, what are vectors good at? They're good at creation, destruction, subscripting, and then adding and removing things, but only at the end there like that. And then they're worse at adding and removing things sort of anywhere else, like inserts and erases either at the middle or the beginning. Those require shifting the existing elements up there like that. So like that's if you're trying to choose a data structure, vectors are good for subscripting and adding and removing things at the end. But if you need to sometimes add and remove things in the middle, you might want to choose something else. Although we'll see later on that like it's not always just like sort of easy of like, oh, I'm adding stuff to the middle of a vector, I should use something different. Like in the real world, there's other factors sort of at play here like that. So it turns out that the same thing that makes subscripting on like arrays and vectors fast is what makes insert and erases slow. So arrays are stored contiguously in memory. They store all the elements like they're the same size and they're all one after another. So that makes it easy if you want to find like the ith item in a vector or an array. You just find the address of the first thing, and for arrays that's just the address of the array there. Then you multiply I by the size of the elements, and they're all the same size, so you don't need to figure out, oh wait, like this element is bigger than the one before it or something like that. It's just multiplying by a constant, and then you add that to the starting address. So the formula to find the sort of ith element there, the address of the ith element of an array or vector, is just the address of the beginning of the array plus I times the element size. So it involves an addition and a multiplication, and those are both simple operations. So that means it takes O of 1 time. But if you want to insert or remove something from the middle of an array, you have to preserve the contiguous nature of it, or otherwise this like wouldn't work, right? So like, for example, let's say you're going to insert something in the middle of an array. you can't just be like, oh, I want to insert this in position 37. I'm just going to put it somewhere else in memory and then give myself like a note in some way that like, oh, by the way, element number 37 isn't where you expect it to be. It's somewhere else there, something like that. If you do that, then now the formula up here, this doesn't work anymore. You can't use that to find the elements of your array. So now subscripting is sort of slow there like that. Same thing goes for like erase, right? If you want to erase an element, you can't just be like, oh, I'm going to mark this spot as like I'm not using it, because then that means that like now things aren't where you expect them to be. So the very same thing that makes subscripting fast also kind of forces insert and erase to be slow. So what we're going to do next is we're going to build a data structure that kind of flips that around here. One that allows us to do fast inserts and erases, but that means that our subscripting is going to become slow as a result there. So a linked list is a data structure composed of nodes, where each node has sort of like two components to it. There's the value, that's what are we actually like storing in the list here, like numbers or whatever they're like that. And then each node has a pointer to the next node in the sequence here. You can think of it as like each node is like directions to where the sort of next node is here. So normally we draw our nodes looking something like this, like the value is on the left and the next is on the right, and the next is drawn with like a little arrow pointing to wherever the next node is actually located there. So like here's an example of how we would draw a list containing 7, -2, 3, 9, and 1 here. And I'm drawing the nodes like kind of spaced out like this to emphasize that they are not like adjacent in memory the way that an array is. When we draw an array, right, we draw it as something like this. Doot, 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 because all the things in an array are just like one after another in memory. In a linked list, that's not how things work. These nodes could be anywhere in memory, anywhere that the sort of like new delete system, the allocator, finds space for them there. In order to use a list, of course, you have to know where it starts, right? Like once you have a starting point, you can follow those next pointers and get to any of the other elements here, but we need to know where is the first node, and that is called the head, which we usually abbreviate to sort of HD. So that's the one thing that we have to sort of store, is a pointer to the first node in the list here like that. We don't have to, but it's also convenient to store a pointer to the tail of the list, the last node in the list there. That lets us sort of like manipulate the end of the list faster than if we didn't have it. If we don't have the tail pointer and you want to do anything involving the end of the list, you have to start at the beginning of the list and sort of follow the chain all the way down to find the tail of the list there like that. So storing that extra pointer for the tail makes operations at the end of the list faster than they would be sort of otherwise. So let's say that we want to insert a new value between 3 and 9. So we're going to insert 0 between 3 and 9. So all we do is we create this new node here, right? And then we reroute the pointers to connect it in the list. And note that none of the other nodes needed to move around. Nothing needed to get shifted. There were no loops. I just create a new node, update 2 pointers, and now that new node is placed between 3 and 9 there like that. Same thing for like an erase. Like let's say we want to erase the node containing the -2. All I do is I route the pointers around it. I make a little detour and then I delete it. And it's gone. Like none of the other nodes need to move. Nothing needs to get shifted around here. There's no like loops or anything like that. It's just update a pointer, delete, and we're ready to go there like that. So our inserts and our erases become much sort of faster here. They don't involve any looping. They're O of 1, not O of n. Now, what did we have to give up to get that? Well, let's say that you want to get to the node over here. So if we number the nodes, this would be node number 0, this would be 1, this would be 2, and this would be 3. So if you want to get to node number 2, you have to start at the beginning, at the head, and follow those next pointers until you find it. So unlike an array where you can just jump straight to any particular value, in a linked list, you have to start at the beginning and kind of like follow the directions all the way down here. So finding the ith node takes time proportional to I there. That's what we gave up, was the ability to jump to just particular elements there. So if we sort of compare them, we can see like who's good at what. If you want to create a vector of size n, it can do that in constant time, unless you want to like fill it with stuff, in which case it would be O of n here. But for a linked list, every node is created individually, so we would have to do a loop to create all n nodes here. When you destroy a vector, you're just doing one delete. But a linked list, each node is a separate new, so that means we need to do n deletes to delete all the individual nodes there like that. Getting the size of a vector, that's easy. We just return the value of sz. Getting the size of a linked list, if you just kind of do it the naive way, you have to loop through and count all the nodes, which would take you O of n. Now, of course, with the list, you could just add to the list an sz variable to track the size, and then that would make that O of 1 as well. So we'll sort of see that later on there like that. If you want to get the ith element out of an array or a vector, that's just O of 1. But in a linked list, that means you're going to be following many next pointers to sort of figure out where it is here. And then the operations that like sort of are inserts and erases. So pushback, adding stuff at the end. For vectors, that's O1 amortized. For linked lists, it's just straight O1. There's no amortized. That is both the best and worst case runtime for our pushback function there like that. It's just always O of 1 here. If you want to do a popback on a vector, that's O of 1. For reasons we'll see later, popback on a linked list is actually O of n, because it's a little bit sort of like there's a little bit of fiddliness with how it needs to sort of work there like that. Push front, pop front, on vectors, those are the slow ones. On linked lists, those are nice and fast. Insert, inserting at a position I here like that. On a vector, that involves shifting, but on a linked list, that's just pointer manipulation there. Same thing goes for sort of erase there like that. We can kind of see like what are the things that like vectors win at and what are the things that linked lists win at. Vectors are good at creation, destruction, pushback, popback, and linked lists are good at insert and erase at sort of general positions as well as pushbacks here. We'll see later in the sort of second part of this module here that there is a way to make popback run in O of 1 time, but it has a cost in terms of memory usage to make that sort of happen there. So here's a skeleton of what our linked list class is going to look like here. So in our sort of private data section, our nodes are structs, where each node again has a value and a pointer to the next here. And then we store in the class pointers to both the head and the tail of the list here like that. Initially, the list is empty, which we represent as the head and the tail both being null pointers there. All right, so first we're going to look at insert. Like, how do we sort of insert into a list here? So in order to insert into a list here, I need a node pointer to the node before the spot where you want to do the insert. And that's because it's A's next that I'm going to need to like change to point to some other thing there like that. It might seem a little bit weird, but I need a pointer to the spot before where you want to do the insert here like that. So that we'll call A. This B over here is the node like after the spot where we want to do the insert, but B is really just A's next. Like I don't take a parameter for B, I just can get there from A. And my insert is going to break down into sort of 4 cases, basically depending on whether or not A exists and whether or not B exists. So the sort of general case is if both A and B exist. They're both like sort of real nodes here. We're going to follow these new steps here. So we're going to create our new node. We'll call it N. So that's going to be something like node pointer N equals a new node. And then we would also probably fill in its value at the same time there like that. So we create our new node N there like that. Then we're going to set N's next to B, which is really just A's next here. So that's setting this thing here and saying you point to that one there. So that's going to be something like N's next is equal to A's next. Remember that we don't have a variable for B, right? Like B isn't a variable, it's just sort of like a thing for the diagram. This is really A's next there, like that. And then what's the final thing that we need to do? We need to update A's next to point to N. So I update this right there and say you need to point up there like that. So that would be like A's next equals N there, like that. Just as a sort of like an aside here, right? Like I'm doing A arrow next, right? I am not doing A dot next. Dot won't work here. And that is because what is A? A is a node pointer, right? A is not a real node. A is a pointer to a node there. So I can't use the dot on A because A isn't a node. If I wanted to, I could dereference A. So I could do star A. Now I have a real node. And then I could do dot next on that. But that's kind of a lot of typing. So the arrow that I'm using here, which is just a minus and a greater than, A minus greater than next, is just a shortcut syntax for star A dot next there. So like the nice thing about linked lists is, yeah, we're working with pointers, but we're never sort of like crossing over between pointers and real things. So you don't have to worry about like, well, when do I use the star and when do I take the address and stuff like that right there. Like we're just going to use the arrow all the time. So everywhere that you think you might want to use a dot, just use an arrow, and that's probably like the right thing to do there. So the end of my sort of rant about that there. That's case number 0, where both A and B are nodes. They're really there. Case 1 is, what if we don't have an A, right? Like what if A is null pointer? So A equals null pointer. Now if A is null pointer, that means I cannot use A arrow next to get to B. Well, the only node that doesn't have anything before it is the head, so that must mean that B comes from the head. So our steps are going to be pretty similar to before, but with just a switch out, because now we're going to be using like the head instead of A's next here. So again, we're going to create our new node N, sort of out there wherever we find memory for it. We're going to set N's next to point not to A's next, because A doesn't exist, but we're going to set it to point to whatever the head points to. Set N's next to point to the head. And then we update the head to point to N, because now N is the sort of new first thing in the list here, right? This case is equivalent to a push front here. So one thing to notice is these steps are just exactly the same as the ones in case 0, but we're replacing B with the head there like that. So it's the same idea, it's just we don't have an A arrow next anymore there. All right, so then on to the next case. Case number 2 is, what if we don't have a B? B is a null pointer. That means we're looking at something like a pushback, because we're adding something, like the only node that doesn't have anything after it is the tail. So if A is the tail, then we're adding a new tail here. So this is going to have an extra step where we update the tail here. The steps are going to be basically the same as in case 0, just with a new step 4 added onto the end here. So we create our new node N. Then we're going to set N's next to null pointer, but that could be A's next. Like you could imagine copying this sort of like null pointer that we have in A's next up there into N. So I could do N's next equals A's next, which is the code from case 0, and it would still work here. It would still do the right thing, the same as if I had said N's next equals null pointer there like that. Then I set A's next. A used to be the tail. I set A's next to point to N. And then there's one final step, which is the tail is now pointing to the wrong node. A is no longer the tail. N is the tail. So my last step down here is to update the tail. The list now has a new last element at the end of it there like that. So 4 steps for case number 2 there like that. And then the last case, case number 3, is kind of like the combination of cases 1 and 2. It's what if both A and B are null pointer. That means that the list is empty. The only way that I could not have a node before or after the spot where I want to do the insert is if there are no nodes at all. That's the only way that that could sort of happen here. So that means that we are creating the very first node here. So we create our new node n. We set n's next to null pointer because it's going to be the only node that exists. So it is going to be the tail, and the tail's next is always null pointer there like that. We set the head to point to n. And then we set the tail to point to n here. So the little note at the bottom here says, like, these steps 1 through 3 here, those can come from case 1, and then step number 4 down here at the end, that comes from case 2. So you can think of case 3 as just kind of like a combination of the two cases that we covered there like that, which should make sense, right? Because case 1 was like a push front, case 2 was like a push back. If your list is empty, the first node you are adding becomes both head and tail, so it is both a push back and a push front there. So this is the code for insert. It looks a little bit overwhelming, I know, but that's just because I tried to write it all out sort of explicitly here. So we'll go over it sort of step by step here. So one thing you might have noticed is that step 1 of all the cases is always the same. So I just pulled that out and put it up there at the top rather than like repeating it inside of each case there like that. So case 0 is located here. We detect case 0 if checking to see if A is not null pointer. So does A exist, right? If A is not null pointer, then B is A's next. So we check to see if B is also not null pointer. And if that's the case, then we do, this is step 1 up here, right? We do step 2 and step 3, just like that. For case number 1, right, case number 1 is A does not exist. A is a null pointer. If A is a null pointer, then I can't look at A's next. So for B, we look at the head instead there. The head is not null pointer. So A doesn't exist, but B does here. So then this is step number 2, and this is step number 3 right there. And notice that like these two steps here are the same as the code up here from case number 1, just with the head replacing A arrow next. So just replace A arrow next with head, head, and you have the code for case number 1 down there. Case number 2, right? Case number 2, the code for this can be the same as the code for case 0. So here we have step 2, step 3. Over here we have step 2, 3, and 4. So I wrote n's next equals null pointer, but you could also use A's next over there because that would sort of work in this case as well. So you could write this as A's next there because we know that A's next is a null pointer in this case here. We have the extra step 4 here at the end where we update the tail. And then our final case, case number 3, right, is if we don't have an A and we don't have a B here. So again, like instead of writing null pointer here, you could write head, making step 2 and 3 the same as steps 2 and 3 from over here in case number 1. And then step number 4 can come from that one up there. You'll notice that like there's no loops in here, right? Like it is a 4-way if else, which is like a little bit sort of like, you know, a little bit to digest all at once there like that, but there's no loops. It's all just pointer updates there. That means all of this is O of 1 time there. It takes a constant amount of time. That doesn't mean that it always takes exactly the same amount of time, right? Like sometimes we do 3 steps, sometimes we do 4 steps there. It just means that the runtime doesn't depend on the size of our list, the number of nodes in the list there like that. If you sort of like, you know, recognize the symmetry between the cases, you can kind of compress them down here like this. So here I have compressed cases 0 and 2 into a single if, and then the else part here is cases 1 and 3. The idea is that like we only ever do step 4 in sort of like some of the time here, so we'll just nest an if in here to detect when do we need to do the step 4 there like that. If you want to get really clever, you can do this. I won't explain this. There's no runtime advantage to writing insert like this as this sort of like, 4 lines of code here like that. But it's a sort of like a bit of C++ magic that we're using in here. So if you want, you can kind of work through this and figure out why this does the same thing as the other previous ones there. I'm not recommending this code, but if you want to get sort of clever, you could write it out like that there. The big O analysis of insert is pretty easy, right? No loops, just pointer stuff, pointer comparisons, pointer updates. So it's all O of 1, but that is assuming that you already have A. You already have a pointer to the node sort of prior to the spot where you want to do the insert there like that. Now, one thing to sort of bear in mind when you're working with linked lists is the order of the steps is really important here. So like let's look at case 0 here. So the correct order is first we update ends next, then we update A's next here. So over here, let's see what happens if we mix up that order. We do step 3 and then step 2. Like we update A first and then we update ends next here. So if we do that, okay, so far so good. A's next points to N. That seems fine, right? So that was this step right there. But then when we do N's next equals A's next, the A's next here has already been updated to point to N. So we're really saying N's next equals N itself. So now we have a cycle. We have a place where N is its own next, and we lose access to everything else in the list that comes after it there. If we try and loop over this list, we'll probably get stuck in an infinite loop here at N here. So like pay attention to the order of the steps here. If you end up with like an infinite loop or something, chances are good that you sort of got something like kind of mixed up like that. So here I'm going to sort of show like what's going on in memory to sort of illustrate like how this kind of works here. So let's say we have a list with just 2 nodes here. So the head of our list has a value of 7, and then after that there's a node 2, and then that's the end of the list here. So the head is 7, so that means the head points to address 3000, that right there, right? And then 3000's next points up here to that one there like that. So the order of the nodes in memory has nothing to do with the order of the nodes in the list here. The order of the nodes in the list is 7, then 2. The order of the nodes in memory is 2, and then a bunch of space that's being used for who knows what, and then 7 after that there. So let's say we want to insert a new node in between these two here. We're going to do an insert in between the 7 and the 2 here. So first we create our new node N, right? So N gets created down here at some other address that happens to be available at address 7000, and we set its value to 1 there like that. Then we set N's next, which is this entry right here, to point to B, which is A's next here. So that points me at address 1000 up there like that. And then finally, we update A's next to point to N. So I have this points here, and then this points up there like that. I didn't have to move either of the 2 existing nodes, right? Their addresses did not change. I just updated the value of that pointer and set the value of that pointer there. So that's why I can insert things without needing any like looping or shifting things around there like that. Okay, now let's take a look at erase. So if we want to erase this node right here, we need to have a pointer to A, because A's next is going to need to get updated to route around it here. So it might seem a little bit weird, but our erase function is going to take a pointer to the node before the node that you want to erase there, like that. We can only go forward. We can't go backwards. So if we had a pointer to n, I would be kind of stuck there like that. So just like insert, our erase is going to break down into sort of 4 cases here, based on whether the node before the node that we're wanting to delete exists, right? So we have A, we have N, and then we have B. We have A and B exist, we have A doesn't exist, B doesn't exist, or neither of them exist there like that. Now, unlike insert, there are a couple of extra situations here where erase doesn't do anything because there's no node to erase. So if the list is empty, then there's nothing to erase. And if A is the tail, right? If A is here at the tail there like that, remember that A erases the node after it, but the tail doesn't have anything after it, so there's nothing to erase there. So in these 2 cases here, we don't do anything. So our erase starts off with an if that just checks for those 2 situations. That if looks like this here. It might not be obvious, but this actually covers both of these cases here. So if the list is empty, that means that the tail is a null pointer, right? But if the list is empty, then A also has to be a null pointer because there's no nodes, right? There's nothing for A to point to. So we have A also equal null pointer there like that. So that covers the case where the list is empty. And then, of course, if A is the tail and the list is not empty, this just sort of obviously covers that case there. So it works for both there. If either of those things are true, we just return. There's nothing to erase, so we don't do anything. Maybe we should like throw an exception or something. I don't know. Returning is just like the easy thing to do. All right, so case 0, A and B both exist, and N is in the middle of the list here, right? There's a node before it and a node after it. There might be like a million nodes before it and a million nodes after it, but I don't care about those. I just care about A and B here. So my first step is to get an extra pointer to N, which is A's next. That's how we get to N, is as A's next there like that. I need my own pointer to N because I'm going to be changing A's next to make it point to B. If I change A's next and I don't already have a pointer to N, now I've leaked memory, right? Like now I have a node floating around out there that I don't have any way of getting to. Then I update A's next pointer so that it points over here. It sort of detours around the node that I'm going to destroy there like that, points to B. And B is N's next or A's next. And then I just delete N. Then I sort of blow N away there like that. So if I'm looping through the list at this point here, I'm going to go A, and then B, and then whatever sort of comes after it there. I sort of never notice that there is anything missing there. Case 1, what if A doesn't exist here? So if A doesn't exist, that means we're working off of the head. We are doing a pop front. We are erasing the head. So we don't have an A, so we're going to use the head to sort of like substitute for it there like that. So once again, I give myself an extra pointer to the head because I'm going to be redirecting the head to point to B. If I don't have a pointer to N, then I'm leaking memory and I don't have any way to get back to that node there. I set the head to point to B, just like I said. And again, B is the N's next or the head's next. That would be 2 ways that I could sort of get to it there like that. Now that there's no connections pointing to N other than N itself, I'm free to delete N there. So a couple of pointer updates and then a delete there. All right. What if B doesn't exist here? So what if B is a null pointer? And again, remember that B is just going to be A's next, or N's next once we have N. So the only node that doesn't have anything after it is the tail. So that means that N must be the tail of the list, and we are doing a pop back here. So just like the case 2 for insert, this is going to have an extra step 4 where we update the tail here. The steps are going to be the same as case 0 with a step 4 added on here. We set n to point to a's next, which is also the tail here. That would also work. Then we set a's next to null pointer. Now I could do that by using n's next or a's next. Like imagine taking this value here and like copying it over into a's next there. So like the same code that worked for step number 2 in case 0 would also work here. Then I'm going to set the tail to point to a as step number 3 here, like that. And then finally I'm going to delete n there like that. The step 4 and step 3 here are a little bit different from case 0, and that's just because I want to make sure that all of the pointers that used to point to n point to somewhere else, and I want the delete to come last here. It's sort of safest to make sure that like I don't have any pointers pointing to the node that I'm going to delete before I delete it there like that. I want there to be exactly one pointer pointing to n when I delete it, so that I don't risk having like dangling pointers or something like that. Case number 3 is the last case. That's kind of like, what if a and b don't exist? So that means that n is the very last node. There's only one node left. I've deleted everything else. So after I do this erase, the list will be empty. So both the head and the tail are pointing at my sort of target node here. If it seems weird that I have the tail on the left and the head on the right, it's just because it makes the diagram easier when we have to update the arrows here in a second. So again, we're going to give ourselves n as a pointer to the head. So this step is borrowed from case 1. We're going to set the head to null pointer, but that null pointer could come from n's next or the head's next there. So this step here is also borrowed from case 1. Then we're going to borrow step number 3 from case 2 that we just looked at, where we update the tail. So now tail is null pointer, head is null pointer. We're ready to go to do the delete of n. So here's our erase implementation here. We've got our check up front to see if we, if we even have something to erase here. And this is my sort of case 0 here. So case 0, a exists, and then b is a's next also exist here like that. So again, step number 1, step number 2, step number 3 there like that. Case number 1, what if a doesn't exist? If a doesn't exist, I don't want to look at a's next, so I substitute heads next as my access for b there like that. Step number 1, step number 2, step number 3 there like that. Case number 2, a does exist, but b does not exist, is a null pointer there like that. So here I have step number 1, step 2, step 3, and step 4. So like if you sort of line these up here, right? Step 1, there and there. Those are the same, right? Step 2, there and there. That can be the same. Instead of the null pointer here, you can use n's next, because we know that n's next is a null pointer from up there. Step number 3 is new, but step number 4 is the same. In fact, step number 4 is the same in all of these. We could sort of pull it out and put it at the end, except that we get n from different places here. Like n doesn't always come from the same place there like that. So you can think of case 2 as just case 0 with like this extra step sort of inserted in the middle of it there when we need to update the tail. And the same thing is true of case 3. If I don't have an A and I don't have a B, the first step of this is like the first step of that. The second step of this can be the same as the second step of that. Like you could use n's next instead of a null pointer there like that. The third step could come from up here, right? That could be A instead of a null pointer there like that. And then the fourth step is, of course, the common fourth step of all of them there like that. If you want, you can merge those together and just sort of like do an if in the middle to determine when you need to do that like extra step 3 in there. When do we need to update the tail? That just makes it into like a sort of two-way if-else instead of like the sort of four-way else out of it there like that. It doesn't change like the big O complexity. The big O is still just O of n for the, O of 1 for the whole thing there. Just maybe makes the code a little bit like sort of shorter there like that. There's like a saying that like, you know, like the number of bugs in your code is like sort of big O of the number of lines of code. The more lines you write, the more bugs you have. And that's true, but you don't want to like, you know, carry it to an extreme where you're writing stuff like this. So this thing here is like simplified, you know, beyond all reason. We're using a pointer reference to do some weird stuff here and collapse everything together to make it just really short little thing here like that. So I'm not saying you should do this. In fact, I don't think you should do this here, but it is a thing that you can do there. If you know, sometimes you need the ego boost where you want to feel like a rock star coder. So you write something like this and you're like, yeah, I still got it. Or maybe that's just me. I don't know. Again, like the analysis for erase is easy. It's all just simple operations, just pointer comparisons and updates. So it all works out to O of 1, but that is assuming that we already have A, the pointer to the node prior to the sort of one that we want to erase there like that. Once we have insert and erase, these sort of helper functions for push back, pop back, push front, pop front, those mostly become pretty easy. So like, how do you do a push front? That's just an insert before the head. So that is an insert with a null pointer. How do you do a pushback? That's an insert after the tail. So that's just an insert where we pass the tail there like that. How do we remove the head? That's just an erase where we pass it a null pointer. That's not erase head, right? Like if you want to sort of like, you know, do a little bit of exercise here, figure out what would erase HD erase and why is that wrong? Why is that wrong for pop front? Like what would it do instead there like that? And since insert and erase are all O1, so are all of these. We get all of those for free because our insert and our erase kind of do all the heavy lifting there. The odd one out is pop back. So a pop back tries to erase the tail, but that is not erase tail, right? We have an if at the beginning of our erase that literally says, if you ask me to erase the tail, I don't do anything. And that's because the parameter to erase is not the node that we want to erase, it's the node before the one that we want to erase here. So to erase the tail, right, if the tail of my list is down here, I need A to be the node before that. And I don't have an easy way to get that other than by starting at the beginning of the list and looping through until I find the second to last node here. So that's what popback has to do. It has to start at the head, loop until it finds a thing whose next is the tail, and then erase that. So this loop here runs n minus 1 times. Inside the loop, we're only doing O1 of work. There like that. So this loop runs in O of n time there like that. Popback is like the weird one out because we don't have an easy way to get to the second to last node in our list here. Some other list operations, right? If you want to get the size of your list, if you don't do anything in particular, you have to loop through the entire list and count all the nodes there like that. So this loop is going to run n times. And inside the loop, we're only doing O1 work. So the total for the loop is O of n. All the other stuff in here is just O of 1. So the total for that would be O of n. Now, of course, there's an easy way to make it O of 1, which is just add to our class an sz variable. We'll increment it in insert. We'll decrement it. Sorry, that should be decrement it in erase there like that. And then the size function just returns the value of sc. So that makes it O of 1 at the cost of an extra int in our class there like that. A linked list isn't an array, and you shouldn't try to treat it like an array, but sometimes you do need to find the ith node given an index I here. So the at function does that. You tell it, oh, I want node number 327, and it returns a pointer to that node. But the only way that we can do that is by looping through the list, and this is going to run I times. So that's going to be big O of 1. Stuff inside of the loop is all O of 1, right? Times I gives me a runtime of O of I. In the worst case, I is at the end of the list there, and then that runs O of n times there like that. So that's why down here I'm saying it runs I or n times, whichever is sort of smaller there like that. So don't treat a linked list like an array. Don't try to subscript off of it there. Use node pointers to track stuff in it. Don't use ints as indexes. When we sort of like, create a linked list, if you want a linked list of a particular size, you have to create all those nodes individually. So creating a linked list of size 1,000,000 requires a loop that runs 1,000,000 times. And the same thing is true about destroying a linked list. We have to destroy all the nodes one by one. So destruction, your destructor is going to involve a loop that takes O of n time. Same thing is true for copying. Your copy constructor, your copy assignment are going to involve loops that go through and copy the node values one at a time into the new list there like that. So those are a little bit slower there. So here's that sort of table again here like that. It's kind of worked out. You can kind of see again, what are vectors good for? They're good for subscripting and pushback popbacks. What are linked lists good for? They're good for pushbacks and then sort of general insert and erases in the middle or something like that right there. There's one other thing that linked lists offer us that isn't like a sort of big O, like a runtime thing here, but it is sometimes very useful. If you go back to the example where we like inserted a new node into the list and I showed what memory looks like, you'll notice that like the addresses of the other two nodes did not change. So that means if you have a node pointer to an interesting node in a list, right? As long as you don't delete that node, that pointer will always be good. Like you can always use it to access that node, no matter what other nodes are being inserted and erased around it. In an array, though, if you have like the index of an interesting value, that isn't necessarily useful. If you insert or erase before it, that changes the indexes of everything after it there. You have to like, update. You can't just use indexes as like bookmarks to keep track of stuff here. So in a linked list, node pointers are stable. If you have a node pointer to an interesting node, that node pointer will always work unless you delete that particular node. You can delete all the other nodes around it. You can insert 1,000,000 new nodes before it. That pointer will always be good there. So sometimes that's a useful thing to have, is the ability to sort of bookmark interesting things and have those bookmarks like still be good later on in your program there. Now, here's the thing that like is kind of an easy mistake to make, right? Is let's say that we want to write a function to print a linked list here. And we're going to take advantage of the fact that we already have a size function and we already have an at function that gives us the ith node here. So we're going to get set I to 0, right? And we're going to say I is less than size, and then we're going to get the ith node and print out its value. So what is the big O runtime of this function here? You might want to like pause the video and like think about it for a little bit here. If you said O of n, that's not correct here. So if we look at this loop here, right? For loops, we work from the inside out. So the runtime of this is O of 1. The runtime of this, well, that depends on how the size function is implemented. That might be O of 1, or it might be O of n there like that. And then the runtime of this involves the at function, which always takes O of I time. There's no way to optimize the at function to not take O of I time here. So this loop here is going to be n times O of I, which works out to O of n squared. It's that same sort of triangular shape that we saw before there like that, where I is like getting bigger and bigger and doing more and more work as we go down here like that. So even though we didn't literally write a nested loop here, we effectively did, because there is a loop inside of the at function, turning this into an O of n squared here. Again, linked lists are not arrays. Don't treat them like arrays here. The correct way to do this would be to get yourself a node pointer to the head, and then follow the nexts and print the sort of node values using that method there. Now, this is what I was mentioning a while back there, that like, if you just look at the table of like who's good at what here, you'd be like, okay, vectors are good at subscripts and linked lists are good at inserts. They're like that. But in the real world, things are a little bit more sort of tricky there. In an array, the elements are just one after another in memory. They follow like a nice predictable pattern. In a linked list, the elements like are not in any particular pattern in memory. So when you loop over a linked list, you're jumping around in memory, sort of like in sort of almost at random as it appears. They're like that. Modern CPUs are really, really optimized for predictable memory access patterns. So if you're looping over an array and you're just being like, okay, I'm accessing this spot and then I'm accessing the next spot and then next spot there, the CPU will kind of pick up on that and will sort of like start loading in later array elements before you even request them, because it can predict the pattern of memory accesses that you're using. With a linked list, though, the pattern isn't predictable, so the CPU can't do that. So that means that even if you're using the right style of loop for a linked list, looping over a linked list might be like 100 times slower than looping over an array. It's still O of n, right? But it's like O of 100n versus just like a O of sort of n, you know, with a smaller constant there. Big O doesn't care about that, but in the real world, that constant that's hidden away inside of the big O can be big enough to like affect your decisions unless your lists are, you know, millions of elements long there. So the advantages of linked lists don't really start to pay off until your list is really, really big, right? You need to be looking at lists with like hundreds of thousands of elements before the sort of like cheap insert and deletes really start to sort of pay off here. If your list is short, an array will actually be better even though it has a loop inside of it there. Like the loop will run that much faster. It's like, oh yeah, I have a loop that runs in n over 100 for an array, and then for a linked list I have a constant time thing that runs in O of 100,000 or something like that, right? I'm abusing the big O notation here, right? So as long as your n is small, then this one here, this is the array version over here, this is the list version over here, right? The array version is going to be better than the list version there. So where that sort of cutoff line is depends on like your compiler optimization levels, your CPU architecture, but it could be anywhere up to like even 1 million elements. Like you can have a pretty big array and still have insert and erase be faster on it in the real world, even though in the theoretical land, Big O says, no, you should be really using a linked list for this kind of thing there. So just in the real world, you know, you have to measure performance. You have to look at like how things really perform, and you can't necessarily just take like the theoretical stuff as gospel there like that. So in the real world, linked lists are used not so much because you need like fast inserts and errates, it's because you need stable pointers, right? You want to be able to like bookmark a thing in the list and have that bookmark always work, or because you need controlled memory allocation. When we insert a new element into a list, we create one node's worth of memory. Like that's always how much additional memory we use there. When we add an element to an array, it might use 0 memory if we already have the capacity for it, but it might use O of n memory if we have to double the capacity there like that. So if we want to control how much memory each insert takes there, linked lists give us that in a way that vectors don't give us that there. So you see linked list used in sort of memory controlled environments where you're like doing embedded system stuff, or like they show up a lot in like the Linux kernel, operating system kernels, they're like that. They're not quite as popular as the sort of general purpose data structure that they once were there. There's another situation that I forgot to mention in here where lists are useful, which is if the actual values are very large. Right? If the things that you are storing are not just integers, but they're like huge things there, then the advantages of an array don't really play out because the things are sort of big enough that they're already far apart in memory. So it's kind of like a wash which way it comes out there like that. So those are the things that I just showed you are called singly linked lists. They have only a single link going forward. So in the next section, we will look at doubly linked lists, which have 2 pointers, one that goes forward and one that goes backward. So that will kind of like, solve the problem of pop back being the weird one out that takes like extra time there. But now we have, an extra pointer to update. Doesn't change the big O, but we do have 2 pointers to update instead of just one. So we'll look at that in our next video, and then that will also be the subject of our second assignment. Assignment 2 is to sort of implement a doubly linked list class. But that'll do it for right now. So thanks a lot for your time, everybody, and I hope you have a great day.